Hello everybody, and welcome back to another video where we will be integrating another Maths 505 integral, specifically the integral from 0 to infinity of sine of x divided by the hyperbolic sine of x, with respect to x, of course. And yeah, so let's get started. This is going to be very similar to the one I did previously on the channel. In some ways, it's actually a little bit nicer, but in others, it's a little bit more annoying, but well, we'll see. So to start off with, as with the other one, we're just gonna put everything in terms of e, or e to the x, really. So what I'm going to do is say that sine of x is just equal to the imaginary part of e to the xi. This just follows from Euler's formula. And for hyperbolic sine, something similar. We just know this is e to the x minus, this time, e to the minus x over 2. And then just subbing those in, we're going to have 2 times the integral, the imaginary part, of 2 times the integral from 0 to infinity of e to the xi divided by e to the x minus e to the minus x dx. All right, so again, as before, I'm just going to swap the 2 out to change the bounds. And again, this is just because of symmetry. And although sine is an odd function, so is hyperbolic sine, which basically means that because both are odd, if you divide them, you're going to get an even function. So, a little tidbit for you. All right. Now, one thing y'all might actually be noticing now is, okay, you have a sine of x and hyperbolic sine. If you plug in 0 here, you might be saying, oh, aren't you dividing by 0? And the answer is, yeah, sort of. You get a 0 over 0. In the limit, it actually is 1, I believe. But we'll cross that bridge when we get there in regards to residues. It's really not that bad to take care of, but we'll see. So, as similar to the cosine one, actually we're going to cross the bridge right now. So similar to the cosine video, we are going to integrate it over a semicircular contour. So something like this, say. But one difference we have here actually is that we do have that 0, or that hole at x equals 0. And the way we're going to get around that is that we're just going to make this a semicircular contour. So basically what we're going to say is it's a normal contour, except for the fact that there's a tiny little bump right there. So we're integrating around the origin, more or less, like over a semicircle around the origin. So yes. So I'm actually going to do something I don't normally do, actually. I'm going to write out properly the entire integral. So we know that our entire integral over c is going to be equal to the integral of over, say, we'll call this 1, and 2. So gamma 1, gamma 2, gamma 3, and I'm going to call this gamma 4. We know that the integral over gamma 1 plus the integral of gamma 2 is the integral of gamma 3 plus the integral of gamma 4. We know that the integral over gamma 1, by Jordan's lemma, that's just going to go to 0. Prove that on your own if you like. And the integral over gamma 2 plus the integral of gamma 3, in the limit, as this semicircular piece right there, as that approaches 0, we know that these two together, because we're adding them, this is just going to be the integral over the entire real axis. So I, if you like, I'll define this up here, I guess. So that's the integral we want. But you will also notice that we have this extra little integral over gamma 4 right here. And this right here is actually going to be just pi I, negative pi I times the residue of f at 0. And the reason for this is because instead of integrating normally counterclockwise around a full circle, we're integrating clockwise, hence the negative, around half a circle, so that it's pi, or pi I instead of 2 pi I. So yes, in the limit, it's going to equal that. But we also know exactly what this evaluates to by the residue theorem. This is going to be just equal to 2 pi I times the sum of all of those residues. Residues at F. I'm just going to call them K for now. We don't know what they are yet. So, based off this, it's really not that bad to see that we can just kind of solve for I here, right? We can just say our integral is just going to be equal to pi I times the residue of F at 0 plus 2 pi I times the sum of the rest of our residues. So I've said the word residue enough now to where we should probably actually calculate it. So yeah, let's do that. Just gonna go up here. All right, so here's our function f. I'll just calculate them up here, that's fine. As before, I'm just going to take the inverse of both sides, or raise it to -1 power, however you like to say that, I suppose. Over e to the xi equals 0. Again, that's never 0, so we end up just getting e to the x minus e to the minus x equals 0. So those must be equal. Let's go multiply both sides by e to the x, meaning we get e to the 2x is equal to 1. Now this time, it actually is a little bit nicer because we're going to take, I suppose, the natural log of both sides, you could say. But I guess more accurately, we're doing this complexly, if you like. So instead of just the natural log of 1 equaling 0, I mean, it can be, but it could also equal, in this case, 2 pi I or 4 pi I, any integer multiple of 2 pi I, because e to the 2 pi I, or any integer multiple, is just going to be equal to 1. So, therefore, we know that we know that 2x is going to be equal to 2 pi I n, meaning x is just equal to pi I n, which is much cleaner than the thing we got last time, which had an extra term with like pi over 2 in it and such. This is just a whole lot nicer. This next part, though, is a tiny bit different and not so nice, but, you know, ups and downs here. So yes. Or we should probably calculate the actual residue, shouldn't we? Those are just our poles. I'm sorry. Yes, so we have e to the x minus pi I n. I'm not going to sub in for k this time. It's not that bad to write out pi I n. Times e to the x I over e to the x minus e to the minus x. And I'm first going to calculate the residues as, well, this is going to be general. As x approaches pi n. I'm going to first do it, first multiply by 2 pi I for the residues, and then I'm going to do the pi I later, because they will give slightly different things. You'll see what I mean. Again, by the L'Hopital's rule, we are just going to get e to the xi over e to the x plus e to the minus x. Just differentiating top and bottom. Don't forget about product rule, but it does, the other term of the product rule does just go to 0. And this is just going to be, these really should be x's, these should be pi n's, I'm sorry. Pi I n. Pi I n minus pi I n. Okay. So what we're going to do now is, we're just going to take a look at this. And that should be a plus, I'm sorry. This looks an awful lot like cosine, because we know that cosine of some x is just equal to e to the xi plus e to the minus xi all over 2. So if we just, multiply this by 2 and divide by 2, it's the same thing, but we can just kind of take advantage of that. So what we're going to say here is we have e to the pi I n over 2 times the cosine of pi n, because we drop the I, it's kind of part of this right here. And okay, we know n is an integer, but what's the cosine of any integer of pi? Well, we can think of it like this way. So cosine of 0, well, that's just 1. Cosine of pi, this is negative 1. Cosine of 2 pi equals just 1. So it's like we're ping-ponging back and forth on the unit circle. So this is just going to be, this cosine term, just negative 1 to the n. So what we have as our residues are e to the pi I n times negative 1 to the n, oh, n. I can not write n today, my goodness. Over 2. These are our residues right here. So I'm just going to plug all this in. I'm going to start with the 2 pi I term right here. Meaning that we have 2 pi I times the sum from n equals 1 to infinity. The reason it's 1 is because for the n equals 0 residue, that is just 0, and we have something kind of special for that because it's not actually in our contour. It's slightly outside it. Hence why I have to do the other semicircle. Times 1/2. So I'm just going to cancel out the halves now, sake of brevity. For e to the pi I n, or I am very sorry, actually. This right here should be I squared, so it's I squared. I am very sorry. I squared. Meaning that in the numerator here, we actually have a negative pi n. I'm very sorry for that. Okay, just gonna fix that real quick. Y'all didn't see that. Shh. Okay. Times negative 1 to the n. This is similar as well to the one last video, but I'm gonna hold off evaluating that real quick. For this one right here, though, we have pi I times, well, this evaluated at 0, which is just, well, anything raised to 0 power is just gonna be 1. So it's just a half. And trust me, that half is very important. So what we have here is this not so nice looking expression, but I'm just going to go ahead and evaluate this bit right here. So this right here equals, kind of throw out the pi I times, again, we can express the inside as negative e to the minus pi to the n, meaning that our geometric series is just going to converge. We plug in 1 here, so negative e to the minus pi, divided by 1 plus e to the minus pi. And that's because you get a minus negative. For more info on geometric series, I'll probably put a link down in the description. Yes. So that's about half of it. So we have pi I over 2 plus our pi I times, or well, I'm just going to put the negative out front so I don't forget about it. Pi I times e to the minus pi, all divided by 1 plus e to the minus pi. And this looks really ugly, but it actually does simplify quite a bit, believe it or not. So first and foremost, we need the imaginary part of this integral, and you'll notice that the only thing making this imaginary is, well, the I here, the I here and the I here, which we can just kind of factor out along with the pi. So what I'm going to say is this is equal to our actual integral, or the imaginary part of it at least, is going to be equal to pi times 1/2 minus, and for this I'm just going to multiply the top and bottom by e to the pi. I'll make things just a little bit nicer. 1 over 1 plus e to the pi. Okay, and for this next bit, I'm just going to clean this up a tiny bit. So I'm going to basically get both of these to a common denominator. So we end up getting this equal to pi times 1 plus e to the pi over 2, 1 plus e to the pi, minus 2. Yeah. Yes, that's right. Okay. Sorry, just wanted to make sure. Okay. And And based on this, we can kind of, well, first thing I'm going to do is actually just kind of factor out the 2 from the bottom, just bring that out. So pi over 2 times, well, 1 minus 2, that's just minus 1, so e to the pi minus 1 over e to the pi plus 1. That looks really ugly, I am going to be honest. But actually, this is a pretty nice function right here, because if we think of hyperbolic sine and hyperbolic cosine, so we know that hyperbolic sine, I know I've already written this, but let's go do it one more time, was e to the x minus e to the minus x over 2. Hyperbolic cosine, on the other hand, is the same thing, but with a plus. So, okay, say we were to divide the 2 to get a hyperbolic tangent, right? Well, that would just be, what, sine over cosine? Hyperbolic sine over hyperbolic cosine. Well, that would just be e to the x minus e to the minus x divided by e to the x plus e to the minus x. But if we multiply the top and bottom by e to the x, we actually end up getting e to the 2x minus 1 over e to the x plus, or 2x plus 1. But, hold on. Those are the same. No way. Just do note that we have an e to the pi, meaning that we need to divide it by 2, because there's like a 2x here. We would express this in terms of the inverse tangent. So, what we have here is actually, our integral is equal to pi over 2 times the hyperbolic tangent of pi over 2, which is really cool and actually very similar to the cosine integral we did in the last video. So, yeah, I hope you all enjoyed and maybe learned a thing or two. And yeah, this has been fun. Thank you for watching, and see you next time.